So I think we can get started now. So I didn't post homework for for the last lesson because I didn't cover everything. So I'll sometime this week I'll put together a handout to cover the missing material, and then I'll post some homework. Okay, so today we're going to talk about solutions. Okay, so um, so what is a solution? So a solution is a uniform mixture. So a mixture of two things, and it's uniform. So it's completely the same throughout. So that means you cannot separate it into its constituents easily. You can't, so it's very difficult to separate solutions. Okay. So this is in contrast with a heterogeneous mixture. So in a heterogeneous mixture, you have different components that can be somewhat easily separated. So for example, you can have gravel. So gravel might be a mixture of gray rocks and white rocks, and you can easily separate these rocks. Or trail mix, and you have like nuts and granola, so you can easily separate those. Okay, but this is a uniform mixture, what would be called a homogeneous mixture. Homogeneous. Okay. So to define a solution better, we can say that a solution is comprised of some solute, which is dissolved in some solvent. So in the example I have here, we have sugar dissolving in some water. So our sugar is going to be our solute, and the water is the solvent. And you end up with this sugar solution. Okay. So there are a lot of different kinds of solutions. We can have gases mixed with gases. So for example, the air would be a solution because we have a mixture of oxygen, nitrogen, argon, carbon dioxide, and a bunch of other stuff. Okay. So we can have gases and gases. We can have a lot of different things dissolved in liquids. So we can have gases dissolved in liquids. We can have solids dissolved in liquids, and we can just have other liquids dissolved in liquids. So, yeah. So here I have a picture of like an ocean, so a coral reef. So the ocean is also a solution. So we have definitely like the salt in the ocean, like seawater is very salty. But also we have a lot of dissolved oxygen and carbon dioxide. So, fish need oxygen to survive. All animals need oxygen to survive. So this oxygen comes from dissolved oxygen gas in the water, and not from the oxygen in the water itself. So there's actually, which a lot of people, it's a misconception. So there actually is just oxygen gas dissolved in the water at a very low concentration. And we're going to have liquids dissolved in liquids too, right? If you ever mixed honey and water, right, they dissolve inside each other. So that would be like a solution of honey and water. Okay. And finally, we have solid solutions, what are called solid solutions. So these are basically like alloys. For example, steel is an alloy so you have like carbon, chromium, and iron with some maybe like manganese in it too. And brass is a mixture of copper and zinc, I think. So just to give you some examples, so these are what are called alloys. So basically you have multiple different metals mixed uniformly together. So you could consider that to be a solution. And I want to differentiate what are called solutions and what are called colloids. So here I have a picture. So on the left-hand side, we have a solution. And on the right-hand side, we have a colloid. So both of them are pretty clear. The difference is that in a colloid, we have particles in what is called suspension. So these are particles that, so like free-floating particles, and they're in suspension. And for colloids, usually these particles are so small that they remain in suspension indefinitely. So like, the water molecules are all bouncing around, so they will keep those particles in the water. But if we have large enough particles, they will eventually fall out of suspension and fall to the bottom, but not necessarily in a colloid. So these particles have diameters with around 2 to 500 nanometers. And a nanometer is 1/1000th of a meter. And colloids exhibit what's called the Tyndall effect. So here we can see we've passed a beam of light through these two beakers. And you can see the beam of light doesn't do anything to the solution. It just passes right through. But the beam of light is scattered by the particles in the colloidal suspension. Okay? So this is why we can see a beam of light here. It's being scattered by the particles. So incidentally, this is why milk is opaque. So milk is a colloid, so you have all of like the milk proteins and stuff suspended in water. So they scatter light, so which is why milk is not clear. Okay, so let's go over some basic vocabulary. So we want to talk about concentration of a solution. So concentration is basically how much stuff per volume of solvent do you have. So this can be in grams per liter, moles per milliliter, etc. You just need to have some unit of stuff per some unit of volume, okay? And then we can apply some qualitative adjectives to concentration. So dilute and concentrated. So this is like a very qualitative, basic understanding of how much stuff you have. So, if something is dilute, you don't have a lot of stuff. If it's concentrated, you have a lot of stuff per unit volume. Okay, so a saturated solution is a solution in which you have the maximum amount of solute per volume of solvent. So if you've ever gone dissolving like sugar or salt in water, you keep on adding it and all of it dissolves until a certain point. And at that point, no more salt or no more sugar will be able to dissolve. So at that point, the solution is what you would call saturated. And we have what are also called supersaturated solutions. So in a supersaturated solution, you have more than the maximum, so more than a saturated solution. So these are what we might call metastable, because if you disturb them, if you disturb a supersaturated solution, all of the dissolved solute will start to crash out. The colloquial term is called crash out. So it will crash out of solution and it will crystallize. So you'll form these like crystals. And usually this crashing out is very fast. So you'll get these very small crystals, almost like a powder. So for example, the ways to disturb it, so you might add a seed crystal. So you might add like a tiny crystal of the solute, and then the rest of the solute will crystallize around that seed crystal. Or another common technique in chemistry is to use a glass stir rod. So like something like this, a glass stir rod, to scratch the inside of your container. So by scratching it, you will form these microscopic chips of glass, which form what are called nucleation sites. So nucleation sites, so Nucleation, I think. So nucleation sites where the solute can crystallize. Okay. Now I want to make an important note that saturated and concentrated do not necessarily mean the same thing, right? So for example, if we consider a solution of silver chloride, so silver chloride is very insoluble in water. So some things are very soluble, so they dissolve a lot. Some things are insoluble, they don't dissolve a lot. So silver chloride is very, very insoluble in water. And so maybe about per liter, you can get 10 to the minus 5 moles per liter. So, and that's about the maximum. So that would be considered a saturated solution, right? Because you can't dissolve any more silver chloride in that. However, this is still a dilute solution because 10 to the minus 5 moles of stuff is really not a lot, right? So that might be just like a fraction of a milligram, right? And on the other hand, you can have like a very concentrated solution of sugar. So like maybe you can add like 100 grams of sugar to 1 liter of water, which is a huge amount of sugar. So it will be very concentrated, but it's not saturated. You can add much more sugar than that to water, and it will still dissolve, actually. Okay. Okay. So I want to talk about the process of forming a solution. So we have a solvent. We have some solvent molecules, and we have solute molecules. So notice how our solvent is going to be like just water, so a liquid. So we have these disorderly particles. Meanwhile, the solute is probably like some solid compound. So it forms these orderly crystals. So the first step is to break these up into their separate particles. So you know these particles have intermolecular forces, so they attract each other. So it takes a lot of energy to break these things apart, right? So now we have these separate particles. And now when we go to form our solution, these particles also will have intermolecular forces. So these particles are also interacting. And this will release a huge amount of energy because so that interaction makes the overall solution have a low energy. So this results in the release of a lot of energy. On the other hand, for some solutions, the solution might actually be pretty high in energy. So you won't release that much, you won't release too much energy when we combine these separate particles. So you might notice that we have the energy of the products, of the reactants, so the stuff that's going in, and the energy of the products, so what's going out. So if what's going out has a lower energy, then the change in energy, so the change in enthalpy, so I should spell this properly. So enthalpy. So it's not strictly the same thing as energy, but you can think about it like that for now. So enthalpy. So the enthalpy in this case will decrease. Hence, the change in enthalpy is going to be negative. Here, we're getting an increase in energy. Our enthalpy is increasing. So the change in enthalpy is positive, right? So remember that delta H, so the change, I should use a different pen. Delta H equals the H of the final state minus the enthalpy of the initial state, right? So here, the enthalpy of the final state is greater than that of the initial state, so it's positive, okay? So there are definitely many examples of both of these two cases. For example, with calcium chloride, so calcium chloride is very exothermic. So if you dissolve calcium chloride in water, it will release heat. So this is why they use calcium chloride to salt the roads in some very cold places like Alaska, because regular old salt won't do the trick. So you need calcium chloride and it will actually heat up. So sodium chloride is actually very slightly endothermic. So it absorbs heat. So it's this case. So just to clarify what exothermic and endothermic means. So in an exothermic process, the delta H, the change in enthalpy is negative. So for an exothermic process, delta H is negative. For an endothermic process, delta H is positive. Okay, so what this means is that for an exothermic process, since the energy is going down, that energy has to go somewhere. So we get a release of energy. So exothermic reactions will often produce heat, right? And endothermic reactions actually absorb heat. So they make their surroundings colder. Okay, so another example of a highly exothermic process would be dissolving sodium hydroxide in water. So if you dissolve sodium hydroxide is very special. So sodium hydroxide is very, very exothermic. So it does get very hot to the touch if you dissolve it in water. And another example would be very strong acids. So like your very strong, very concentrated mineral acids. So your sulfuric acid, your nitric acid, your phosphoric acid. So this is why in the laboratory, you have to be sure not to add water to acid. Because if you add water to acid, it will very quickly heat up. So the specific heat of the acid, I guess you can think of it like how much energy you need to heat it up is very small. It's not very big. So it will heat up very rapidly, and it might start to boil. So you can get hot concentrated acid splashing in your face. So very dangerous. So you need to add acid to water because water has a very high specific heat. So a water can safely absorb some of that extra heat and it will not boil. Okay. Okay. So one note on delta H, so change in enthalpy. So let's look at these three reactions. So A goes to B, and this reaction has a delta H of A, so delta HA. This reaction, B to C, has delta HB, and A to C has, that should say delta HC. C, okay? Right, okay. So enthalpy is a state function. So it doesn't matter how you get there. It doesn't matter how you get to a certain state. It will still have the same enthalpy. So an analogy would be like an object on a bookshelf. So an object on a bookshelf is some distance above the ground. So it's some height above the ground. So it has some what we would call gravitational potential energy. So the gravitational potential energy is equal to the mass times the gravitational constant, so little g, times height. So higher objects have more energy, lower objects have less energy. So imagine an object on the top shelf of your bookshelf, and imagine an object on the lowest shelf. So you can go from the low shelf to the middle shelf and then the high shelf, or you can go from the low shelf directly to the high shelf. Either way, you still need to input the same amount of energy, okay? It doesn't matter how you get to the high shelf, it will still require the same amount of energy. So it does not depend on the path you take. Thus, we can say that delta HA plus delta HB equals the delta HC, okay? Because this two-step process still goes from A to C, so it must be the same as this. Okay, so this principle is called Hess's law. So we can see it, and just one minor note. So the reaction of B to A, so reversing the reaction will make the delta H negative, right? So if going from a low state to a high state has a positive delta H, going from a high state to a low state will have the equal negative delta H, right? Same magnitude. So we can see this. So this is called Hess's law, this principle that we can add these delta H's, okay? So you can see this here. So suppose we know this reaction, we know this data, and we know this data. So we can calculate this because, so first of all, this is going in reverse. So this path, let me label this just to make it easier. So A, B, and C, okay? So A goes to B is the same thing as A going to C going to B, right? So we already know the value of C going to B, but now we need to find the value of A going to C. Well, we know the value of C going to A because, and it's given to us. So all we need to do is make this, so we have to reverse the sign. So this should be positive 483.6. So going from A to C will have a delta H of 483.6 kilojoules. And then for C to B, we can just sum these. So C to B is just negative 393.5. So A to B is going to be the sum of that. So A to B is going to be 483.6 plus negative 393.5, right? Okay. So yeah, this just, okay. So here's a problem. So maybe like just a few minutes. So I want you to estimate the enthalpy of solution for silver chloride. So estimate how much energy, estimate the delta H of this reaction, okay? So here's the data you're given. So we're given the lattice energy of silver chloride. So this is the energy released when a silver plus ion combines with a chloride 1 minus ion. So Ag plus Cl minus goes to AgCl. So we're given that this is negative 916 kilojoules. And the enthalpy of hydration, so basically the enthalpy of hydration is like when we go from silver plus to silver plus aqueous at what's called infinite dilution, okay? But you don't have to worry about what infinite dilution means. So all this is just saying this is the energy we get when water molecules interact with our silver ions, and likewise for the chloride ions. So with this information in mind, you can estimate this enthalpy. So I'll give you a minute to do that. Okay. So what data are we given? So we are given the data for the reaction. So we're given the data for the reaction Ag plus Cl minus goes to AgCl. So we're given this data, okay? So we're given that this has delta H equals negative 916 kilojoules. 2, we're given this data. So aqueous, so dissolved in water. So AQ stands for aqueous, S stands for solid, right? So this is given delta H equals negative 473 kilojoules, and we're given this Cl plus goes to Cl. Oh, that should be Cl minus. Cl minus. So delta H equals negative 378 kilojoules. Okay. And by the way, this is per mole. Per mole. Okay. So we need to find the delta H for this reaction. So does anyone have a suggestion on how we can calculate this from the above data? So, well, we have that we're starting with AgCl. So we need to start with some reaction that has AgCl in it, right? So clearly this is the only reaction with AgCl in it. So this would be a good place to start. So the problem is that AgCl is on the product side. Well, we want AgCl to be on the reactant side. So the best way to do that, so all we need to do is reverse reaction 1. So we've simply reversed this reaction. So this is delta H equals negative 196 kilojoules per mole, right? Because if we reverse a reaction, all we need to do is to flip the sign of delta H. So now we have Ag plus and Cl minus on the product side, which we need to get rid of since we want Ag plus aqueous. So this is technically gaseous, I think. So gaseous. Okay. This is a G, by the way. So so we can just to get rid of this, we just need to use this. So and then Cl minus. Right. What happens when we sum all of this together? So what happens when we take the sum? So I've drawn a sigma. Okay. So you'll notice this cancels out and this cancels out. So we're left with this. Right, which it turns out is what we want. So that's what we want, and then the delta H is just the sum of all of this stuff. So the sum is 65. And one final question. So we've calculated our delta H. So do you think it will require energy? Do you think the dissolving of silver chloride absorbs energy or releases energy? So does this process absorb or release energy? So we've calculated the sign of delta H. So does this absorb or release energy? So remember that delta H equals the enthalpy of the final state minus the enthalpy of the initial state. So that means we're going from, so since this is positive, this is clearly going to be bigger than this, right? So our final state will be at a higher enthalpy than our initial state. So it takes energy for us to go up in enthalpy. We need to add, so we have an increase in enthalpy, which requires an input of energy, right? So okay, so we require an input of energy. Okay. So does everyone understand how I did this calculation? Okay. So I want to talk about another factor that impacts the formation of solutions. So this is entropy. So salts are these ordered crystals, so our ionic compounds. So these are our very ordered crystals. So we have a rigid crystal structure. Okay. By contrast, particles in a solution will move around very freely, so they can move however they please, and there's no overall long-range order. This means that we have an increase in this disorder. So when a compound dissolves, we will usually have an increase in disorder. And this disorder can be called entropy, so which is indicated by an S. So S here. So when we have an increase in entropy, we have a positive delta S, okay? And in general, according to the second law of thermodynamics, the entropy of the universe is always increasing. So, so looking at these pictures, we can see which one happened first. So we always want to go from a low entropy to a high energy, since entropy will always increase. So this has low entropy, this has high entropy. So therefore, the system will move in this direction. So this direction, it will move from right to left. And this is because of like statistics. Okay, statistically, it should move from right to left. Okay. So what makes substances soluble? So we want a negative delta H. So here I've written the delta as a D, since you might see that sometimes. So a more negative delta H means that we're releasing more energy, okay? So if it had a positive delta H, we would need to input energy to make the reaction go. But exothermic reactions already produce energy, so yeah. So a negative delta H is good. And a positive delta S is also good. Sometimes your value for delta S might be very small, so close to 0, or sometimes in rare cases, delta S can even be negative, because these ions in solution they interact with the water molecules very strongly. So these water molecules start to form these kind of shells around the ions, what are called solvation shells. So the positive end of the water molecule will form a tight shell around the negative ion, or vice versa. So this might increase the order, it might decrease delta S. So yeah, so these two factors will make substances more soluble. So we want a negative delta H and a positive delta S, okay? So here's a problem. So multiple choice. So when potassium chloride, so this is an example of a problem you might see on the AP exam, right? So when potassium chloride dissolves in water, the water gets cold to the touch. Which of the following can be concluded from the following information, from the above information? A, the entropy increase overcomes the unfavorable heat of dissolution. B, potassium chloride is relatively insoluble in water. C, the entropy decreases when potassium chloride dissolves. And D, this is an exothermic process. Okay, so just what letter do you think it is? Oops. Ooh. Here. So what letter do you think it is? Let's start with the first part. So when potassium chloride dissolves in water, the water gets cold to the touch. So it gets cold. So what does this tell you? So what information do you know from that? So what information do you know from the fact that it gets cold? You can unmute your microphone if you want to respond. So if the temperature is decreasing, that means that you're absorbing energy from the surroundings, right? So you have to absorb energy from the surroundings. So if we have an absorption of energy, that means that the enthalpy is increasing, right? So what does that tell us about the sign of the delta H? If we're increasing the enthalpy. Should be positive, right? Because if we're increasing enthalpy, the enthalpy of the final state will be higher than the enthalpy of the initial state. Hence, the delta H will be positive. And So if you look at the previous slide, oh, wait, why is it doing that? A negative delta H is more favorable. So a positive delta H is pretty unfavorable, okay? So we can rule out D since we've already established that delta H is positive, hence it's an endothermic process, not an exothermic process. Let's look at the other choices. So B is probably wrong since the problem never actually mentions mentions the solubility of potassium chloride. So we can't make any conclusions based on that. And from experience, and actually, if you know your solubility rules, you'll know that potassium chloride, so I have a bottle of potassium chloride right here, is very soluble actually. So potassium chloride is very soluble in water. So that's not true, okay? So the entropy decreases when potassium chloride dissolves. So let's evaluate this claim. So if we have a decreasing entropy, what's the sign of delta S? If our entropy is decreasing, what's the sign of delta S? Is it positive or negative? So delta S should be negative if the entropy decreases, right? So yeah, delta S means change in entropy. So obviously if you decrease entropy, the change will be negative. So, so that means if this statement were true, we would have a negative delta S and a positive delta H. Both of these factors make are unfavorable. So that would mean that the dissolution of potassium chloride would be very unfavored. But that's not true since we know that it does dissolve, right? When it dissolves in water. So we cannot conclude that that's true. Also, that's fairly rare, so that's not a super good choice. So therefore, the correct answer should be A. So it's true that we have an unfavorable heat of dissolution, but this unfavorableness can be overcome by the fact that we have a very favorable increase in entropy. And when we study thermodynamics, we'll be able to quantify this favorableness, okay? So next, I want to classify solutes. So we have different kinds of solutes. So first, we have a non-electrolyte. So these do not conduct electricity. So for example, glucose, which is a kind of sugar, and ethanol, so alcohol. So these will both dissolve in water, but they do not conduct electricity, okay? Then we have strong electrolytes. So we have, these are your ionic compounds, which when you dissolve them in water, they completely split into ions, okay? For example, sodium chloride. So when you dissolve sodium chloride in water, it will split into sodium ions and chloride ions, right? Okay. So these will conduct electricity very strongly, okay? And then finally, we have weak electrolytes, which are the most complicated ones because these compounds only partially ionize, usually about less than 10%. For example, your weak acids and your weak bases. What do I mean by partially ionize? Well, here we have a generic weak acid, so HA. And when we dissolve HA in our water, so some of it, so we will form some H plus, some hydronium ions, and we will form some A minus ions. So these ions will conduct electricity. However, we still have a lot of this stuff remaining. So we have a mixture of all four of these things, right? And it's only partially turning into these things. And later, we will learn how to quantify this, this mixture using what are called equilibrium constants. And believe it or not, we can actually relate these equilibrium constants to ideas about enthalpy and entropy, right? So everything in chemistry is interconnected, so which over the next few lessons we will see. So I want you to classify these four solutes. So tell me, is it a strong electrolyte, weak electrolyte, or non-electrolyte? So 5 minutes, I guess. And just post the answers in the chat. Tell me the 3 different types of electrolytes, just to make sure you guys remember. Right, so non-electrolytes, strong electrolytes, and weak electrolytes. So vinegar is a weak acid, right? So vinegar is not a strong acid, otherwise we would not drink it as food. So vinegar is a weak acid. So that means it's a weak electrolyte because it will only partially ionize, okay? Now, NaCl, when you dissolve NaCl in water, it totally becomes ions, right? So what do you think NaCl is? Is it a non-electrolyte, a strong electrolyte, or a weak electrolyte? Strong, right? Great. And sucrose does not dissolve, does not split into ions at all. Sucrose is not an ionic compound. It doesn't even have ions in it. So what does that mean? Great. So what about magnesium chloride? So magnesium chloride is a compound of magnesium, a metal, and chlorine, a nonmetal. So magnesium chloride is an ionic compound. So what do you think magnesium chloride is? Great. So magnesium chloride is a strong electrolyte because it's an ionic compound which will dissociate into ions. So let's take a 10-minute break now so we can come back at around 8 o'clock. So 8 o'clock, okay?